Okay, hey, welcome back. This is now chapter 6, kind of new stuff. If you took me last semester, this is stuff I wouldn't have gone over. Okay, so 6.1, what are we doing now? Differential equations. Basically, solving for, you get an equation and you solve for a function. So before you used to get an equation, you solve for a number. Now we're just taking that up a notch. Okay? So let's get a definition for a differential equation. Let's just get that out of the way. Differential equation. It is an equation in terms of, so an equation in terms of x's, y's, and derivatives of y. And you can use other variables too. A little weird in differential equations, they use x instead of y sometimes. It's confusing. So anyways, and derivatives of y. What do they kind of look like? They'll look like maybe something like this. Y double prime plus y prime plus y equals sine x. Would be an example. There's some extra definitions, so eventually you want to be able to classify differential equations, and you'll have all these methods for solving each different class. So this thing, you could tell by the first term, it's a second order differential equation. Okay. Because of this double derivative here, the second derivative. Let's look at another example. It's y triple prime plus 3 equals e to the x. Then this would be a third order differential equation. Once you get into the class, because there is a class in differential equations, you'll want to be able to classify them also as linear or nonlinear, and that sort of stuff. So for a nonlinear equation, you may have like the derivative is squared or something crazy like that. Okay. It seems to me that in the real world, most of the differential equations will be nonlinear, and you kind of have to have these qualitative methods for solving nonlinear equations, at least back when I was going to college. And the methods we'll look at in this section are more along the lines of these sort of approximation methods for getting solutions. So in general, you're not going to be able to get this perfect solution. And it's a little misleading in that way. All differential equations at this point in time is a little misleading in that way. But anyways, we want to give you kind of the history and be able to do these simple problems. Okay. So if you're still kind of mystified, don't worry. You've already dealt with differential equations. Whenever you do an antiderivative, that you're doing a differential equation. So, for example, if you have dy over dx equals, I don't know, sine of x. What is y? You just find the antiderivative. The solution of this thing, which is a differential equation, you could also write it, y prime equals sine of x. The solution to that is just, like I said, the antiderivative. It's just negative cosine x. That would be a particular solution. In general, you'd have to go a plus c. So you're going to be looking for particular solutions in your work eventually, but this with the plus c is a general solution. So that's that family of curves. And then if you say, all right, negative cosine x plus 2, this would be like a particular solution in that family of curves. Okay, so it's really nothing new. You've dealt with it. It's just we're going to make it more complicated. So maybe another example. dy over dx equals 2x. So this one's pretty simple, and I'm going to be using it as an example here throughout the section. What is the antiderivative of 2x? Well, it's just x squared, right? It's a parabola, x squared plus c. Okay? Okay, so there's that. So getting back to this idea, it's kind of a similar, the education of this is kind of similar to the progression of the education of just equations in general. So if you recall your educations with regards to equations, you probably started here with problems checking solutions. So even before you were solving these things, you would have something like this. So check to see if x equals 1 is a solution to this equation. And you would do that, right? You could say, 3 times 1 plus 2 equals 3 plus 2 equals 5, and therefore it's a solution to the equation. Okay, that was before we could figure out how to even solve these things. And that's kind of how it's going to be right now with these differential equations. I mean, you can solve them, right? Like this guy, we obviously know the antiderivative, but compare that to this guy, where all I do is add in a y. Okay, we don't know how to solve this. Y equals, I don't know what, right? So there's going to be methods that you just don't know about yet, and you're going to have to learn them in time. We don't have them yet. So now, in the beginning here, what we're going to do is kind of give you some sort of differential equation, and then you have to check to see. So a differential equation like y prime equals 4y, and then you have to check to see if y equals something like c e to the 4x is a solution. Okay. So the way we're going to do this follows along with the differential book that I usually teach from. There may be other ways, but it's kind of like doing a trig proof where you start on one side and you get to the other. Start on the right side, work to the left side. Okay, you could work with each side independently, but you can't like move things from one side to the other side and use the equation as a traditional equation, if that makes sense. Okay. So let's look. Okay, so this is part 2 in this section, just checking to see if it's a solution to a differential equation. Okay, checking solutions. So part 1 was the definition. Part 2, I'm just looking at checking. Okay. So let's look at an example. Here we have y prime equals 3y, and I want to see if the equation y equals c e to the 3x is a solution to that. Okay, so usually you can kind of just substitute in, right? That's what you used to do. You just took this, oh, I'm going to put this in here and it works. Now you're different, okay? You don't have all of the material to get this done, but you could use what you know from calculus. You can take the derivative. So this stuff right here is given, okay? And you could use it, you could solve for c, you could take its derivative and use that to get from one side to the other side. Okay, so if you take its derivative, c is a constant, you get c e to the 3x right back times the derivative of 3x, which is 3. Okay? And then you use that to go from one side to the other side. So I'm going to start, and you start on either side that you think that you can work to get to the other side. I'm going to start on the left-hand side. So I'll abbreviate that LHS for left-hand side. And you start there and use algebra and the given information to get to the right-hand side. So starting on the left-hand side, I have y prime, which equals, now I have to use the given information. Okay, so y prime equals 3c e to the 3x. And then that equals 3 times, well, the c e to the 3x is given as y. And we've done it. So this one's pretty easy, right? So, which is the right-hand side, which is what I wanted to show. Okay. Okay, it's pretty simple, right? Okay, so let's look at some variations on this theme. So maybe some harder ones. So an example, a second order differential equation, y double prime plus y equals 0. And I want to check to see if y equals c1 sine x minus c2 cosine x is a solution. So again, you can use this given information to kind of fill in the blanks as you go through and do your proof. So I need y double prime, right? So y prime is c1 cosine x, derivative sine is cosine. This will be negative negative eventually because cosine's derivative is negative sine. So that'll be plus c2 sine x. And then y double prime I need is going to be negative c1 sine x plus c2 cosine x. Okay. Okay, so here I go. I'm going to start again on the left-hand side. So I have y double prime plus y, and then I use the given information to try to get to 0. And, you know, basic rules of addition and stuff like that. Okay, so y double prime is negative c1 sine x plus c2 cosine x. And then y is c1 sine x minus c2 cosine x. And these cancel, and you're just left with 0, which is the right-hand side. And that's what you were trying to show, which shows that this is a solution. Okay, so let's look at a hard one. Okay. So y prime equals 2xy all over x squared minus y squared. Okay. And the solution they're saying is this kind of elliptical type looking thing, x squared plus y squared equals cy. Okay, so you know, I'm going to go from the left and hopefully get to the right. So I'm going to need the derivative y prime. In order to get y prime, I'm going to have to differentiate the given equation with respect to x. Okay? So implicit differentiation. So I have 2x plus 2y times y prime equals c times 1 times y prime. Then I need to solve for y prime. So I'll go and move the 2y over. So I have 2x equals cy prime minus 2y prime. I'm going to flip-flop sides and factor out the y prime. Then solve for y prime. Okay. Okay. So starting on the left-hand side, I note y prime is equal to, from the given information, 2x all over c minus 2y. Now my goal is the right-hand side, right? So I need to get it in this terms of x's and y's. And right now I have it in terms of x, y's, and c's. But I could use the given information to get rid of that c, right? So I'm just going to amend my little box here and take this thing and solve it for c, right? So x squared plus y squared equals cy. And you can solve for c, so you get y equals x squared plus y squared all over c. Okay. Okay, and then I'm just going to, whoops, I was supposed to solve for c. Sorry. I was thinking about something else at the same time. Ugh. Sorry. So this would be over y. And that's what c equals. So now I can use all of this, you know, all of this junk as given information. I can now rewrite y prime as 2x all over c, which is x squared plus y squared over y minus 2y. I could multiply top and bottom by y. Okay, so I'll have 2xy all over, so what am I doing? I'm multiplying this by y and this by y. I have to distribute. So in the first distribution, the y's cancel. And you'll have x squared plus y squared. In the second distribution, you have minus 2y squared, which equals 2xy all over x squared minus y squared, which then is what we were trying to show. Okay, so which is the right-hand side, which is what we wanted to show. Okay, that's our quiz 4, by the way. So this would be the first 4 problems. Just write them on a piece of paper or multiple paper, take pictures of them, upload them, convert them to PDF, and then send it to me on Blackboard. Usually I'm just checking to make sure that you're doing what I do, and if you did, I'll give you full credit and you automatically got 4 points and you don't have to worry about it. If not, you're gonna lose points. So if you didn't do it my way, if you didn't do the problem at all and just wrote the answer or something, you're not gonna get full credit. And odds are, unless you missed things, I'm not gonna send it back. I'll just send back +4. Okay. So 6.1, we want to prove this problem. Let me just write it in my notes so I know what I'm looking for. And that's the 4th part. So one piece of paper for the 4, 5.7 quiz, 5.8 quiz, 5.9 video quiz, 6.1 video quiz, all on one sheet of paper. Send into my email. Okay, that just proves to me that you've been watching the videos like you're supposed to. Okay. Okay, so like I was going on about back here, you can certainly solve a lot of differential equations. As a matter of fact, in the homework, a good deal of the homework problems just use integration to solve the differential equation, right? So let's maybe look at maybe 1 or 2 of those for a second, and then we'll move on. Okay, so maybe I should title this section 2, solving with integration. And it's not always going to work, right? Because if you have a more complicated problem, it won't work. But if you have something like dy over dx equals some function of x, we'll say u of x, you could solve this with integration. Okay? You just have to find the antiderivative. And let's take a look at the homework over here. And did I forget? Yeah, I forgot to do the initial condition problems too, so I'll do one of those here in a sec. But let's take a look at solving via integration. Okay, so this is number 9 in WebAssign. We have dy over dx equals e to the x all over 8 plus e to the x. Okay, so essentially it just comes down to integrating. If you'd like to, you can think of it as kind of integrating both sides with respect to x. Okay, so what you end up with is the integral of dy equals the integral of e to the x all over 8 plus e to the x dx. And because the dx is kind of cancel out here, if you want to think of it that way, that's the way you think of it. It's not technically correct to think of it that way, because in higher dimensions you'll have issues. But anyways, the integral of 1 dy is just y, and then on the right hand side you have an integral to do. So u sub, obviously, or hopefully, kind of obviously, for 8 plus e to the x. And the differential is e to the x dx, and then dx is du over e to the x. Okay, so on the right hand side we're getting e to the x over u times du over e to the x. So these cancel, and you're left with a natural log, du over u. So we get the natural log of the absolute value of u, your integration constant, and then back sub. So the solution is the ln of the absolute value of 8 plus e to the x plus c. And if you look on WebAssign, look, they don't write absolute value. So that made it something to think about, you know. Why don't they write the absolute value? Because the x is always positive, and anything positive plus a positive is positive, so you don't need the absolute values, right? Okay. Oh, I forgot to do the initial condition problems. Okay. So you're going to see in the homework a bunch of these crazy ones where maybe you have to figure out. Let's look at this one here. So number 4, some of the curves corresponding to different values C are given. Find the particular solution that passes through the point shown on the graph. Okay. So we have y equals c e to the negative x over 2, and they give you the differential equation 2y prime plus y is 0. Actually, you don't even need the differential equation to do this. It's kind of a red herring type problem. To get the to get the particular solution that satisfies the initial condition, you're just going to take that 0, 4 and plug it in. So y, you have 0, 4, you plug in 4 for y and 0 for x. Negative 0 over 2 is just 0. So c will equal 4, right? Because e to the 0 is 1. And so your particular solution is 4e to the negative x over 2. And that would be the answer for that problem. Let's look at one maybe that's a little bit more again, this one here is another red herring problem. You just plug the 3, 4 in there. This one looks a little bit more complicated. So let's take a look at this one. This is number 6. We're given, again, this general solution. And it's a second-order differential equation. So to get the particular solution, you need 2 initial values as opposed to 1. Again, you don't need the differential equation to actually get the answer. All you're going to need to do is first, you're going to end up with a system of equations, right? So you'll have from y, c1 sine 3x plus c2 cosine 3x. That's equal to 26 when x is pi over 6. So c1 sine of 3 times pi over 6 is sine of pi over 2, which is 1. Plus c2 cosine of 3 pi over 6 is cosine of pi over 2, which is 0. So you end up with c1 is 26. And then you need the derivative to get c2. Okay, so y prime is going to be, with the chain rule, 3c1 cosine of 3x minus 3c2 sine of 3x. And again, you know that y prime is equal to 26 when x is pi over 6. So you have 3c1 cosine of 3 pi over 6 is just going to be 0 minus 3c2 sine of 3 times pi over 6 is sine of pi over 2, which is 1. So C2 apparently we'll have negative 3C2 equals 26. And then solving for C2, you get negative 26 over 3. And then you could plug C1 and C2 in for your final answer. So working with this, y equals C1, which is 26 sine 3x, plus C2, which is negative 26 thirds cosine of 3x. Okay. Okay, so yeah, same kind of problem. Okay. Okay, so that's how you deal with the initial conditions to get your particular solutions. And all you're doing is solving for C. Okay, hopefully that's kind of clear. I kind of screwed up my notes there, but okay. So moving on. now, you're not going to be able to, like I said, solve these all with integrations. So looking back in my notes, I gave you some examples, right? So here, I could solve it by finding the antiderivative. Here, no. Okay. Later on, you'll get methods for solving things like this, but right now, no idea. And in general, when you get the nonlinear, no idea. Maybe AI, there's AI methods that I don't know about now, but hand methods, no. Okay. So what you're going to do are use approximation methods, and for us, we'll have slope fields, which is kind of an analytical method. Am I on section 3? Yeah. Okay, so the first kind of analytical method, and this works with nonlinear systems, differential equations, slope fields. And there's a guy, I think his name is Strogratz. I may probably butchering, but he does a lot of books on calculus. His big claim to fame was working with fireflies and looking at the periodicity of fireflies, because apparently they kind of communicate with each other and they'll sync up. I think he actually wrote a book called Sync. So if you're super interested in mathematical modeling and working with differential equations, this is the guy. He's at MIT. He's big time important. I can even Google him right here. Strogratz, or some variation on that theme. Maybe it's Strogratz. Sync. Yeah, so I spelled it right. Strogratz. Sync. He also does some calculus books, and they're pretty easy to read. I mean, it's fairly easy, but if you got a summer off, and it's a summer, and you're going back to maybe to the university. And you want kind of a layman's approach, or just even a big picture approach to calculus and differential equations, Strogratz is a great guy to read. Okay. So anyways, slope fields. So what are these things? These are kind of graphs of the solution curves, kind of. What it really is the graphs of a bunch of little slopes of the solution curves. Right. So remember, if we had the derivative with respect to x of y equaling 1 over x, what is that thing? That is a natural log, right? So y would equal the natural log of the absolute value of x plus c, and you could graph the solution curves. Okay? So the solution curves is not what we're interested in, though. But you could get the solution curves from the slope field. So the solution curves would look like this. And then the slope fields basically just give you little tick marks on these. So it looks kind of like a maze of sorts. I'll get a picture here in a second. The blue things are the slope field, okay? And you can get them straight from the differential equation. You don't have to solve it or anything. You can get these little tick marks, and that will be your slope field. So let me show you an example from WebAssign of what these generally will look like. So you'll have some tick marks up here and stuff. Where's WebAssign? Okay, so here, this thing in blue is a slope field, and you could draw it by using that differential equation. Okay, you just you could plug the points into that equation and get the slopes. For example, at the point x equals, so we'll say this point here at maybe 1, 1. Okay, so this point is 1, 1. To get the slope of that blue line, what you do is plug that 1, 1 into this differential equation, right? So if you plug 1, 1 in there, you get a slope of 1. 1 over 1 is 1. And then you can see the slope of that line is kind of 1. You go up 1 over 1, right? So slope, rise over run. So I go up 1 and then over 1. And that's kind of the slope of that little tick mark. So you use this differential equation to kind of populate the whole picture with a bunch of little tick marks, and you can figure out the tick marks by using the points in the plane. You just plug the points into this and you're good. Okay, so let's look at one such that we know the answer and see the process kind of pan out. Okay, so an example, y equals 2x. I talked about this one earlier, or rather y prime equals 2x. So we know the answer is y equals x squared plus c. Right? Okay, parabolas. So let's to make a slope field, what you do is just basically literally pick some points. So I'll just pick these 9 points here around the origin. You can see it's easier with a computer because you get millions and millions of points and you can draw it out like that. Okay, but here I'm just using these 9 points, and then you do a table, right? So you do x, y, and y prime. Okay. And for the little tick marks, you're just getting the y prime. Okay, so the 9 points, -1, -1, -1, -1, 0, -1, 1, 0, -1. Sorry. 0, 0, 1, 1, 1. Make a big table. And then what you're doing is plugging the points into the differential equation. Okay? So in this case, y prime is 2x. So I don't even need the y components. I just need the x components. So if I plug in -1, I get -2. So down 2 over 1. And these are all going to be the same. If I plug in 0, I get 0. So horizontal slope, horizontal tick marks. If I plug in 1, I get 2, up 2 over 1. And then I could go to the picture and draw little tick marks for the slopes, right? So if I go to -1, -1, 1 down here, I need a slope of -2. So I go down 1, 2 over 1 and kind of draw that out. And then these are all the same. For the middle ones, they're all 0. So they're just horizontal tick marks. And then for the last ones, it's up 2 over 1. So 1, 2 over 1, kind of draw that like that. And you know, if you just put in tons and tons of more tick marks, you kind of get the picture. And what is the picture? Well, what do you think it is? It's parabolas. If you draw, you know, sort of like following the tick marks, you get parabolas. So you can, and I haven't solved anything. All I did was use the differential equation, and I can get an idea what the picture is. So it's kind of like an analytical way of cheating these problems. Even if you don't know how to get the antiderivative, you can cheat and get a picture of it. Okay. Okay. So for example, this problem here in the homework, they give you the slope field, but let's see if we can kind of figure out. So we have x minus y, and then they're giving us a table of pre-populated. So -4, 6. Oh, geez. Okay. So you have your x, your y, and your y prime. -2, 2, 0, 6, and then you get these y primes. So how do you get the y primes? You just plug the xy into the differential equation. So in the book, you'll probably see that they re-express the differential equation as an equation in terms of x and y, right? So it's a multivariable equation. And then you're plugging in first -4, 6. So that'll be -4 minus 6, which is -10. So we're really, you know, down 10 over 1. So it's really going downwards. And you can see on the picture 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, they're really going downwards in that region. -2, 2. So if I plug in f of -2, 2, I'll have -2 minus 2, which is -4. At 0, f of 0, 6 is going to be 0 minus 6, which is negative. What did I do? This should be -4. Sorry. This will be -6. Okay. So it's kind of going down really, really rapidly, and then it's not as much, and then it starts going down rapidly again. Let's look at 1 over a more 4, 6, right? Let's look at 4, 6, and we probably predict it's going to be positive, but I don't think it is. It's at -2, right? 4, 6, 4 minus 6 is -2, so it's still going down a bit. Probably if you go like 8, 1 right here, you're going to see it's going up again. Okay, okay, so there's that. Then another one here. Yeah, clearly when it's when you have something like what would this be? 4, 2, 4, 6, 8, 10, 12, 14. Yeah. So at 4, when y is 4, you'll have 4 pi over 8 when you put it in, and cosine of 4 pi over 8 is a cosine of pi over 2, which is 0. So you have a 0 slope there. And then it's just matching slope fields. Okay, and then there's the Euler's method. Okay, so that's one qualitative method. Never underestimate these qualitative methods. We sort of frown upon pictures in mathematics, at least some professors do. I have been known to. But these are very powerful when it comes to nonlinear equations. Okay. And again, in general, you're not going to be able to solve a lot of these differential equations by hand. We'll try to convince you otherwise, but anyway. So the last method we'll have for kind of approximating is a numerical method called Euler's method. Let's see, 4. Okay. Please tell me I've been recording. My voice is starting to go. Okay, Euler's method. Like the Houston Oilers. I'm older, so I remember all the old football teams. It's not Euler, it's Euler. It's pronounced weird. Okay. Okay. So, anyways, Euler's method uses it's kind of like Spider-Man, right? So you can imagine you have you're trying to get an idea of the curve, right? And Euler's method is going to give you kind of a polygonal approximation to the smooth curve. Okay, what does that mean? So I'll start somewhere in the plane, and you know, at every point in the plane, you'll have this differential equation, dy over dx, just some usually multivariable function of x and y, and you could plug in that point, you know, whatever one. Maybe it's 1, 2 here. You can plug that into the differential equation and get a slope, okay? And then you could draw kind of a little slope there. So maybe it's positive 1, right? Okay. And then you imagine you're kind of like Spider-Man. You're going to use that slope to get to the next point. So you're going to move over some what they call change in x value or h value, and you use the slope to get to that next point. Okay? So like Spider-Man, you kind of shoot your web from here to here. Okay? And at this next point, you're going to put that into the differential equation. It's going to give you a new slope. So maybe this time it's going down a little bit, like this. And then like Spider-Man, you shoot that to the next position, and you get another segment of your kind of solution curve to the differential equation. Okay? And so here you could do it again and again and again. Maybe now it's going a little bit back up. Maybe it's like a sine curve. So here I am. I got the slope tick mark using the differential equation. Spider-Man shoots it to the next point. Okay, and so on and so forth. Right. So it's a polygonal approximation. That means it's kind of like this. Atari version of maybe what the true solution curve looks like. Maybe the true solution is like this, you know, and usually it's going to not be exact, right? But the shorter kind of the approximation is, and the shorter the web kind of segments are, the better the approximation. Okay, so if you instead from going, maybe if this is 1, you're going by ones. If you go by 0.1s, you'll get better approximations to the solutions curve. Okay, so that's the idea. We need a formula for how to do this, and it's pretty simple. Basically, you're going to start at some x0. Okay, so let's say, and then you'll have some y0. So let's say it's, for the sake of sanity, I'm starting at 1. Okay, and then y sub 0 will be some other place. Maybe it's at 2 in this picture. Okay. And so what do we do? The change in x is always the same. So you're going to have some like change in x or an h value, and let's say in this case it's 1. Okay, so x sub 1 is going to be 2, and then y sub 0 is going to be the previous y height, so I'm at 2, plus the rise part of the rise over run of the slope. Okay, so we get the slope from the differential equation. That's going to be f of x sub 0 comma y sub 0. You just take the point and plug it in to get the slope. Okay. But you don't want the run part. You just want the rise part, right? So you're going to multiply it by the run, which in this case, the run is going to always be 1. It's the change in x part, okay, or the h if you'd rather. Okay, and then you just keep repeating that over and over. So x2 would be 3. Whoops, this should be y sub 1, and then y sub 2 will be y sub 1 plus h times f of x sub 1 comma y sub 1, and so on and so forth. And you keep going. Usually they tell you how many steps they want. Okay. Okay, so the Euler's formula then, the actual formula that we're going to use is as follows: y sub n equals y sub n minus 1 plus h times, I guess they use a big F in the book for the derivative, and those should be n sub 1s in there. Okay, let me correct that. So the first one, x sub n minus 1, y sub n minus 1. Okay. Okay, so again, this f, you're given y sub 0, your x sub 0, some sort of step size, h, and the differential equation, which we're going to think of as f of xy, some sort of multivariable function. And then you get your answer. Okay, so let's try one. Y prime equals x plus y. The starting position, y of 0 is 2. The step size is 0.1. So the smaller the step size, the better the approximation. And we want to go through 10 steps. Okay? So we essentially what you're looking for then, if you go 10 steps, you're trying to figure out what is y of 1, right? Okay, we don't know what y is. And as far as I know, unless you went to school in a different country and already learned differential equations, you have no way of solving this right now. Okay, so this gives us a way of solving. So what we do again is just another table. Okay. We start at 0. X sub 0 would then be right here. Okay. This is x sub 0, and then this is y sub 0. Okay. So x sub 0 is 0, y sub 0 is 2, and then we go by 0.1, right, for 10. And we're typically not going to be after the graph, like the picture, like I drew up here, the polygonal approximation. We're not after that. We're after kind of the final place. So in this case, we're going 0.1, 0.2, 0.3. So this is the one we want. What is y when x is 1, right? Okay. So you could do it by hand. Usually I just do it with my calculator after I get it, that sort of thing. Let's see it by hand, though. It's instructive to kind of go through the process at least once in your life. X sub 0, starting at 0, and then y sub 0 is 2. X sub 1 will be 0.1. So y sub 1 is y sub 0, 2, plus h, which is 0.1, times f of x plus 8, f of x comma y, which is a differential equation, which in this case is x plus y. Okay. So where did I get that? That's right here. Okay. Okay. So x plus y, and you're doing x sub 0 plus y sub 0. So in this case, it's 0 plus 2. And then I could do that by hand. That's 2 plus 0.1 times 2, which is 2 plus 0.2, which is 2.2. Okay, so our first guy is 2.2. And then x sub 2 is 0.2 now. So y sub 2 is the previous one, 2.2, plus 0.1 times 0.1 plus 2.2. A little more work. And then usually you can just put it into your calculator and keep on going. You should get I think it's 693. 2.9923, depending on how many decimals you want. 3.33, 3.71. So I hope the more you go in math, the more you're going to hate approximations, and you're going to be looking for true answers. 5.17, 5.78, if such a thing exists. Right. So y of 1, at the end of the day, if you go through the rigmarole, x sub 10 is 1, and or actually it's x. Which one am I on? Yeah, x sub 10 is 1, so y sub 10 should equal 5.78. Okay. Okay, this is something you want a computer to do for you. Like I said, it's good to have an intuitive notion of how it works, because literally you can make up your own methods. I mean, think how stupid this was. I used Spider-Man. Let's think in terms of Spider-Man and use that to develop this high-powered method, right? I think in truth they probably don't even use Euler Method. They use like I don't know what it's called, like something like R2K method or K2R, I don't know. But this gives you an idea of even how that method works, which is a little more complicated. So if you want to, you can go online and look for, higher power versions of Euler's method. Anyways, let's go online, real quick, and you can see we have one of the Euler method problems in the homework. I hate to show you this, but you can actually, there are calculators there, planetcalc.com. So all I did was Google Euler calculator, and this one seems to be what I want, and Euler method. So y prime, we could do the same problem we just did. So you could put in x plus y. The initial x is 0, the initial y is 2. We want to approximate 1, and then the step size is, we don't know the solution, so we'll get rid of that. And then push calculate, and then, there it is. 5.78 was our answer. And it even does the whole table for you, which is kind of cheating. You want to do this by hand at least once or twice to get your idea of how it works. So let's see. X sub 7 was 4.15. x sub 7, 4.15. Yeah, I got it. Okay. So yeah, at least go through it once. Make sure you know how to do it, and then you should be good. Okay, and we'll leave you there. Thanks for watching, and we'll see you again next time.